All right, hello everyone. Welcome to lesson 1.4 here for AP Stats. We're going to be talking about representing a quantitative variable with graphs. During this video, we won't actually be doing much practice. It'll be me kind of introducing and overviewing things. And then to conclude the lesson on the Nearpod, you will go ahead and do some practice by creating some representations of quantitative variables. Okay? Let's go ahead and get started. So today is all about quantitative variable displays. We have spent part of this week looking at categorical variable displays, both in tables and in graphs. And today we start moving towards quantitative variables, those numeric variables. And right now in our Unit 1, we really are thinking about variables, this language of variation. Statistics is here to help us understand how things vary. When we collect data, we might end up collecting slightly varying data depending on our sample, and the distribution of that data, how it falls within that variable or those variables, might be different. So we are continuing to look at the types of variables and the ways to display information about types of variables, and today we are asking the question, how do we display quantitative variables? We really are looking at univariate data here, really, for the most part. And as a reminder, just would like you to sort of think about these two definitions again. Remember, quantitative variables can come in kind of two flavors. They can be continuous. Those are variables that can take on any value between its minimum and maximum value. For example, the weight of a firefighter. I'm not asking that you actually write this down into your notebook. Actually, should have said, like we have been doing, you need to make sure your page is set up to take notes, and you have the correct entry in the table of contents. You do not need to take notes on this page, but I did add a detail because some people seem to be, which makes sense, confused a little bit by the idea of continuous versus discrete. Continuous variables like the weight of a firefighter, that can be kind of any value, any decimal or fraction thereof. You can keep chopping at smaller value of the variable. Think of it as it doesn't come in any set levels or values. Weight can be anything, 137.25674.926 pounds. Like it could be whatever, right, within some range. That's a continuous variable. If for some reason we were stuck only having weights that go by whole pounds, then it would be a discrete variable, but weight doesn't work that way. Discrete variables are variables that can only take on certain values. For example, shoe size. They come in whole and half numbers, or for example, the number of flipped heads. If you flip a coin a bunch of times and I ask how many heads did you get, you will give me a counting number or a whole number, 0 to whatever you stopped. So we got to think of discrete variables as coming in set value levels or set levels. I do want you to practice with this. I want you to read this question and then answer the prompt that pops up on the video. Which of the following describes a continuous variable? Go ahead and read the choices and answer the question. All right, let's go ahead and get started. So in this case, you should write down the question and the answer choices because we're going to label some things on them. All right, so write down the question and the answer choices. We're going to label some things on them. We want to talk about a continuous variable. So something that doesn't have just set sort of chunks or levels. The number of items sold at a craft booth for one day, this is going to be discrete, right? You're going to sell either 1, 2, 3, 4, 5, 6 different items. It's discrete. You sell whole number items. That's going to be the possible values of that variable. The number of apps downloaded from a website one day. That's also going to be discrete, huh? You're not going to download half an app. It either downloads or it doesn't download. If it fails to download, you don't download half of it. You just fail to download. So it will also come in only whole number increments. Diameters of the tree trunks at an evergreen farm. This doesn't come in sort of set levels. This is going to be our continuous variable, right? If you measure the tree trunk, the diameter of the tree trunk, it could be any range of values from, I don't know, depending on the type of tree, like, you know, a couple millimeters to a couple feet, or not a couple, well, maybe a couple feet depending on the evergreen tree. So this is going to be a continuous variable, and it can take on any values between those sort of millimeters to a couple feet depending on the tree trunk. It could be 1.72564 feet across, right? That is a possibility. So this is going to be a continuous variable here. Number of baskets made by a basketball player, that is also going to be a discrete For just counting the number of baskets, that's got to come in whole numbers. And the shoe sizes of all shoes that is on sale at a department store, this is going to be discrete because that's going to come in whole or half increments. All right, so here's an example of continuous variable in comparison to some discrete variables. Now I want you to do the same thing with the second practice question. Data will be collected on the following variables. Which variable can be considered discrete? Copy the question down in the answer choices and answer the prompt that pops up on the video. All right, here we were talking about discrete variables. The height of a person, that can vary and doesn't come in set levels. So this is continuous. The weight of a person, that can also vary continuously, right? You don't gain weight in half-pound jumps or 5-pound jumps. You gain weight continuously or slowly, or you lose weight continuously or slowly. The length of a person's arm span. This is also continuous, right? You could have an arm span that's 5 feet and 8.276 inches or something like that, right? It's going to come on a continuous spectrum, not in these sort of increments. The time it takes for a person to solve a puzzle. That is also going to be continuous, right? That stopwatch could stop at any fraction of a second. The number of books a person finishes reading in the last month, if we're talking about actually finishing a book, you either finish it or you don't. So this is going to be discrete. It comes in whole number book chunks. We had a lot of examples here that were all whole numbers, but discrete variables don't have to be whole numbers. There could be situations where we actually have to measure stuff by quarter numbers or things like that. So our discrete variable is E here. All right, so let's talk about the different types of displays of quantitative data. We're going to start with the dot plot. And I know there's a lot to write on some of these slides, but I do want you to take the notes and do a quick example here. A dot plot represents each observation within your data collection by a dot, with the position along the horizontal axis corresponding to the data value of that observation, with nearly identical values stacked on top of each other. So for example, in this display, let's say we were collecting data on 40 people, how long they eat breakfast, and we're rounding to the nearest minute. All right. If we're rounding to the nearest minute, that becomes a discrete variable, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 minutes or whatever. And we would put a dot for each person and how long it takes them to eat breakfast. Notice there's 1, 2, 3, 4, 5, 6 dots at the 0 minutes, which means there are 6 people who take less than 30 seconds to eat breakfast, or maybe don't eat it at all. Here, at the 10 level, 1, 2, 3, 4, 5, 6, 7 individuals ate breakfast at 10 minutes. Again, we're rounding to the nearest whole minute in this example. So the steps here for these dot plots is we draw and label the axis, so we want to know what exactly we're measuring. We want to scale the axis depending on what is appropriate. In this case, we're just counting by single minute increments. And we want to plot the values. Make sure there's 1 dot per individual typically, and that they're evenly plotted. We don't want the lines to wiggle. We don't want the dots to vary in size. We want everything to be to scale and even. All right. So here's an example of a dot plot. Kind of a basic comparison of information, almost like a visual tally system. Next up, we have the histogram. The histogram is a chart that measures the height of each bar shows the number or proportion of observations. So this one's a little different because a histogram can show a proportion of observations, because remember that's like a rate. It's a relative comparison, the percent or rate. So a histogram can measure percents or rates. The height of each bar shows the number or proportion of observations that fall within the interval corresponding to that bar. If we alter the widths of the intervals, we can change the appearance of the histogram. I'll get to that in a little bit. So here is a frequency histogram of people's ages. Notice the ages are done in 10-year chunks. So this bar represents people from 20 up to 30 years old. There were 2 people. Between 30 and 40, there were 4 individuals who were counted. Between 40 and 50 years old, there were 4 individuals who were counted. 50 and 60 was 5 individuals. 60 and 70 was 3 individuals. 70 to 80 is 1 individual. No one in 80 to 90. And between 90 and 100, 1 individual. Again, I want you to copy the words down and the example down here. So this would be an example of a frequency histogram. We're just measuring the counts. Now, when you make a histogram, you got some choices to make. You need to define what the intervals are. And one of the big questions is, do we include the boundaries? So on this example, I have included the lower boundary, so including 20, but up to and not including 30. If someone is 30 years old, I push them into this column. You're in the 30s, from like 30 to 39 years old. 39 and 364 days, if you will. Then the next bar is 40 years old, up to, but not including 50. So you will need to, as you make these things, define, at least for yourself, what your intervals are and whether or not you're including those endpoints. So what do I mean altering the interval widths can change the appearance of the histogram? Well, if you're displaying data, you're trying to convey some information. And depending on what that information you want to convey is, you might choose different interval lengths for your display. But you got to be careful. Oh, actually, sorry. We'll get back to that in a second. I was like, well, this is in the slide. That's on the next slide. No wonder. The key here is the intervals. So we want to pay really close attention to that, as I mentioned. We're going to talk about the dangers of changing the widths later on. Here's an example of another histogram. Let's say each month you measure how much weight your puppy has gained or lost, and get these results when you place them in order. That's how many pounds. I should make that more clear down on my chart here. In pounds. How many pounds your dog has gained or lost each month you measure them. All right. And based on this data, it seems like, just looking at this, we're going from negative 0.2, so that's going to be the lower boundary. That's our lower boundary, up to 1.6. It seems like, maybe an increment of 0.5 is what makes sense. That's how wide the interval will be. So I've decided to create this chart here where our lower boundary, since I do have at least 1 month where my dog lost some weight, to go from negative 0.5 up to 0, from 0 up to 0.5, and so on and so forth. So we can actually see this. Between negative 0.5 and 0, there was 1 count. Between 0 and 1.5, there were 1, 2, 3, 4, 5 counts. Notice in this histogram, I did not include 0.5 in this column. I included 0.5 in my next column over, the one right here. In the 0.5 to 1 column, there are 1, 2, 3 observations. None in the 1 to 1.5. And then up to 2, which looks like my maximum increment upper boundary here. There was 1 observation, which is the 1.6. So you need to define those intervals and make sure you're counting in the right number of frequencies or relative frequencies within each interval. It is also important that in histogram the bars are together because you're talking about intervals that flow together. Don't separate the bars. That's a bar graph. That's for categorical variables. Histograms, quantitative variables, the bars come together. For the histogram, altering the interval widths can have a really big impact on the visual representation. Up here, the 0.5 interval was probably pretty good. If I wanted to, I maybe could have broken it down even smaller to like 0.25. But then I would have ended up with maybe some gaps, more of these gaps in my display. So the 0.5 made sense. Here are displays of the same data actually with different intervals. You want to choose the interval width that best represents what you want to convey without being misleading. For example, this first graph where the interval width is 20 makes the data look really symmetric. But if I expand that we're actually measuring on intervals of 10, we're measuring grades here, we get a better look at the data that actually there is more data that we collected that falls in the sort of 80 or less category. It's not really perfectly symmetric. Now if we shift those boundaries, we also get something interesting here, right? This display on the right might not be great because we end up with these sort of flattening of some of the edges here, which maybe doesn't show quite the nuance that you want, right? Especially if you're measuring grades. Well, going up to 105 maybe doesn't totally make sense if you're capping out at 100. So you want to choose a display that helps you see all the information you want about the data without being misleading or displaying things about your data that are not true, like maybe you don't have people that are up to 105%. In general, the steps of creating a histogram, and I'm spending more time with histogram because it's one of the more common ones to see, we'll choose equal width intervals. They have to be equal width intervals. We want to make a table that shows the frequency or relative frequency. Remember, relative frequency means percentage of data points or proportion. When we see that phrase, we're talking about percent or proportion. So you might count that 30% of the data falls into this interval, and that's okay to do if you're going to do relative frequency kinds of things. We make a table that shows the frequency or relative frequency of individuals and chunk those things into the intervals. Then we want to draw and label the axes. We want to scale the axes. We want to make sure that the tick marks are on even intervals, not like even numbers like 2, 4, 6, 8, but on standard increments. And then we want to draw the bars. You want to make sure that they are touching. A histogram is our quantitative representation, so we want to make sure that the bars are touching. All right. Note, if you do use percentages or proportions instead of counts, you want to use, percentages or proportions instead of counts if you're comparing distributions with different numbers of observations. Sometimes it makes sense to have histograms like side by side, basically. Well, in those situations, if you have some survey that had 200 people and you had some survey that had only 40 people, the bars are not going to be a straightforward comparison if you just compare counts. So in that situation, you probably want to use percentages or proportions if you have different sizes of data. Your sample sizes may be different in different experiments or surveys or whatever. So in that case, if you would want to use percentages or proportions if you're comparing data with different numbers of observations. Otherwise, the bar lengths, if you just compare counts, will be radically different. All right. We also have the stem and leaf plot. You probably have seen some of these before. The stem and leaf plot. In a stem and leaf plot, each data value is kind of split into what we call a stem, the first digit or digits, and a leaf, usually the last digit. So let's say I collected the ages of 11 people at some, event or something. I got this information. I'm going to go ahead and make what's called a frequency table. That's oftentimes a good thing to do for this quantitative data. You can do it for the histogram too, and help you chunk these things into classes, if you will, intervals. And I went ahead and graphed over here in a histogram a representation of the data. All right, I chunked it into groups and then made a histogram to represent that data. That is a quantitative variable. And notice it follows all of our rules of histogram stuff. There are intervals. I found out the frequency of people, of individuals within each interval, and graphed those things using equal intervals, bars pushed together. But that's not a stem and leaf plot. We can do a stem and leaf plot for this information, though. For the information we see here, I could, so notice I have it in order already. Sorry, 12, 13, 21, 27. I can go ahead and make a stem and leaf plot for that data. All right, you first arrange the stems from lowest to highest. So in this case, counting upwards, we go down. And then the leaves are arranged in increasing order going out. Notice that our ages, they were 12, 13, 21, 27. The 1 represents the 10th digit, so 12, 13, 21, 27, and the leaves extend in ascending order. All right. It is important in most situations to add a key to explain the meaning of the stems. I gave a very bare example here, but you would probably want to add a key that says the stem is 10's digit, leaf is 1's digit, the variable we're measuring is age. All right. So we do want to make sure we label everything appropriately. All right. You can also split stems up for a better display if you find out that some stem is like really long. Let's say maybe you took a survey and turns out that half of the people are in their 30s. Well, it may actually make sense to chop the stems up and say, hey, our stem is actually going to be, our first one's going to be from 10 years old to 14 years old, and then another one stem that is from 15 to 19, and to kind of chop things up a little bit. Sometimes that can be useful. All right. Here is an example of a back-to-back stem and leaf plot. Notice that in a back-to-back stem and leaf plot, it's actually relatively easy to compare distributions. It looks like before whatever the treatment or something was, we had a display that looked like this. And then after the treatment, we have a display that looks like this. So it looks like whatever we're measuring here, if we kind of just do a general observation, looks like the center decreased. Before, the center seemed to be up here in the 40s maybe, and afterwards the center seems to be over here in the 30s. This is where having your labels is really important. Again, you want to try to come up with a key on the side if possible that can represent for us what the stem is. So maybe the stem here is what would be maybe a good thing to measure. The stem here is time it takes to run the shuttle run, which is a little standard workout thing, in seconds. Actually, we should be more specific. The stem would be the tens digit. The tens digit of the time to run the shuttle run in seconds. The leaf, leaf, if I can spell that, is the ones digit of the time to run the shuttle run in seconds. And the variable we're measuring then, I won't write this whole thing out, I think you get the point. The variable we're measuring here then is the time to run, etc., in seconds, right? You want to make sure you have a key so that people can understand what's going on here and title your graph. All right. Almost there, y'all. The cumulative graph may be a new one for you. It represents the number or proportion of a data set that is less than or equal to a given number. We often call these cumulative frequency graphs. And you got to think of them, cumulative means things piling up. For those of you who have taken calculus with me, you might remember me saying that. Cumulative means things piling up. So essentially this graph is keeping track of how much stuff is less than or equal to a certain number as we move through the values of our variable. Let's say I measured the hair length of a sample of 40 babies and we're doing it in millimeters. So to draw a cumulative frequency graph for the frequency table below, we want to make sure we get the table first. So here's the data I collected and how many babies had hair length within each of those things. I could make a stem and leaf graph here, or like a dot plot, sorry. I guess I could make a stem and leaf plot if I wanted to, if I had the raw data. Could make a histogram, different things I could do with it, but let's do a cumulative frequency graph. So I keep track, there's my frequencies. We need to add a class that has 0 frequencies before the first class in here so that we can kind of see the increase that leads up to that first piece of data that we actually have. Notice that I've also defined in here the class boundaries. That the class boundary at the top of the first one is 15.5, and then anything above 15.5 millimeters I pushed into the second category. There it is, sort of in inequality notation. And then I'm going to measure the cumulative frequency. Well, the cumulative frequency works like this. In the first interval I've defined, there were no individuals. So cumulatively, I have no individuals. In my second interval, I had 2 individuals. So total, I've already passed 2 individuals by the time I get to this point. My next interval had 4 individuals. So cumulatively, 2 plus 4 gives me a total count of 6 total people so far. Then my next total here, my next interval has 8 people. So the total is 2 plus 4 plus 8 for a total of 14 individuals I've collected so far. Then 2 plus 4 plus 8 plus 14, by the time I get up to this boundary, which is 30.5 millimeters, there's a total of 28 individuals. And so on and so forth. You're keeping track of the total number up to that boundary. So by the time we get to this last boundary, the total people up to 45.5 millimeters is the sum of all these, which happens to be 40 total people. Here's what that cumulative frequency graph would look like. We plot those individual points, the cumulative total up to each of those points, and connect them with a smooth curve here. Notice I shortened the interval here because we weren't starting at 0. And then starting at 10.5 up to 15.5, and I'm using those boundary marks that I defined on the last slide, and then just counting how many people are there cumulatively up to that boundary. And we keep track of the total number until we hit our 40 total individuals. Sometimes people will do these as bar graphs too, but the idea is basically to keep track of a running total up to the boundaries that are defined. All right. Visual displays, graphic displays are really fun. I really like them. And there are many, many additional ways that people have developed to display graphically distributions of quantitative data. There's a whole world out there you can explore of how to represent these kinds of things. There are some really cool ones out there. I want to point out one just to kind of give you a sense of the fun. I think it's fun out there when it comes to displaying these quantitative data sets. So here's an example. I love this. This is what's called a flow map. Charles Joseph Menard was known for his ability to combine quantitative data and geography kind of together in these like infographics. And he invented what we now think of as the flow map. This is my favorite one. Let me move this over so you can kind of see what's going on here. Maybe throw it to the other side. This is a map that depicts Napoleon's army size during his failed attempt to invade Moscow in 1812. Now, it actually does much more than that. The graphic is in French, but it does much more than that. The width of these colors, these like bars that spread across, the width of those things indicates the size of his army at that individual time. There's actually numbers measuring the size of his army. And it shows in the direction where his army was walking at different times. All right. In fact, this infographic goes much deeper than that. It's in 2 dimensions because it's flat, but it has 6 types of data. It has the number of Napoleon's troops, the actual army sizes, so that's quantitative. The distances that they're traveling, that's also quantitative. The temperature at the time, so you can start making up conclusions about how the temperature affected the size of his army. As literally they were marching to Moscow in the winter, people died, freezing to death and starving. So the temperature was important to keep track of. The latitude and longitude is also kept on here, as well as the direction of travel and the location relative to specific data, or to specific dates. Actually, let me recount that as 1, 2, 3, 4, 5. Wait a minute. Napoleon's army size 1, 2, 3, 4, 5, 6. Yes, cool. I counted right. It's actually quite impressive. This is I don't know. This is definitely my top 3 graphs, visual representations of quantitative data. I know you maybe don't keep track of your favorite ones. I do. This happened to be in the one of the writing nooks at Carleton College when I was there. I love just looking at this thing. I didn't even know French. I would just look at this thing. I thought it was just like so cool. And I don't know. I just hope that sometime you get a chance to look at some graphs or some visual representations of data and just go, damn, that looks good. Because that's how I feel every time I see this one. Here's actually that flow map laid out over a map of the actual geography they were covering. All right. When they got to Moscow, and then the black represents their return back from Moscow. Notice how small the army was in comparison to the initial army. There were a lot of people who died over the course of this attempt to take Moscow. All right. So that's it for today. Today, you'll spend the rest of the time practicing on Nearpod, actually making some displays. Hopefully you get a chance to feel a little better about these kind of displays. It is a little time consuming. I'm not going to have you do a whole ton right now to do it by hand, but it is helpful for understanding the nuance of how to create data displays, all right? And it is a skill you need to know. If you have trouble doing it on the computer, text or email me and I'll give you directions for I want you to do it by hand and turn it in, all right? Take care, everyone, and I'll see you next time in class. Have a great weekend.